first of all, to start to the Ullmans and all those at HSBO for this wonderful, professionally organized event. They keep calling me an old hat here. I guess maybe that's because I've attended and presented at the last 3 conferences. So I'm feeling a little comfortable up on the stage, but with all the time I've been around and seen the faces, it is always a pleasure to be back. Last year in Portugal, I spoke about hybrid USVs, or hybrid small craft, and was pretty negative on it. I said it just doesn't work, you can't do it, based on a lot of the publications and stuff that had been out in outside in the press. And so I wanted to turn that around today, this year, and I wanted to say where the application of hybrid or diesel-electric technology in a small craft does work and where it does provide an advantage. So this is actually a positive presentation where if anyone viewed mine from last year as being negative. The technology hasn't changed very much in the last year, so all we're looking at is the different ways that we're doing it. So last year we looked at a 7-meter rib and we tried to go 35 knots, which is pretty commonplace these days. We looked at a diesel-electric and a diesel-only option as 2 different variants. We compared their relative endurance at wide open throttle. How long could each platform maintain 35 knots? You don't really use boats that way. Okay, so what? It was just for a point of comparison. We evaluated propulsion systems in a series structure, and I'll talk to a series in a minute. And series is the type of diesel-electric arrangement. It's essentially what a submarine has. We've been using this for 100 years now. The technology's been around. So this first pie chart that's up here was just to show the baseline plant that we looked at, which was a gasoline engine-driven submerged propeller. The lightship weight was 75% of the craft weight. The fuel was 10%, and the cargo was about 15%. We looked at a diesel-electric in series, which you can see the 2 other options that we have on the left. One of them was, what does it take to actually get an electric boat to go 35 knots? And we found that we could do that, but we can only do it for 9 minutes. If we put any more batteries on it than that, the boat would sink. The next one we looked at was a diesel-electric where we said, okay, let's just have a single silent mode of operation, which is good for stealth, good for moving around quietly, and of course it's great for emissions. And we found that we could go 11 knots for 4 hours. Well, you're never going to catch a bad guy at that speed. So we had to come up with something else. We had to look at it a little bit differently because those just weren't feasible. So what we decided to do this year was to look at an 11-meter boat. I call it a USV, but it doesn't have to be a USV. The reason I chose USV is because then I don't have to carry any people, and it's the weight which kills these projects. You can carry people. You can put an operator on a small boat with diesels, engines, and batteries, and electric motors, and you can do a mission. But it makes it easier for us designers if you consider a USV where you don't have to carry people. I looked at a little bit different bias of operational state. I looked at 95% of the time operating at 5 knots and 5% of the time at wide open throttle. So basically we're in a loiter mode with the ability to interdict at high speed. And I also changed the structure of the diesel-electric system to a parallel system as opposed to a series system. In the series system, it means the battery comes out of the power comes out of the generator, goes into the electric motor, and then it goes down to the propeller. On a parallel system, you have actually a diesel engine and electric motor side by side, and one or the other can power the propeller. It's called a parallel system. So this is just a little map to show what the difference of the operational profile does to you. Last year when I mentioned 100% of the time of wide open throttle, that would have been well over here on the left-hand side of the chart. Oops, that's the wrong button. Sorry about that. Let's see if we can go back. There we go. It would be over here on the left-hand side where it says fuel consumption. And you can see that in this particular case, the traditional diesel or the traditional propulsion system burns the lower amount of fuel. That's because the engine is operating where it's designed to operate all the time. As you go to the right, what you see is that that's when you're operating more at low power than you are at the high power, and that's where the diesel-electric or the hybrid system can bring an advantage. And the more hours you use the boat, or the more hours you use all the boats in the fleet, the smaller that delta, that difference needs to be before you start to save money. And that's the important thing today. Everybody's well aware of the state of the economy is around the world, and we're all looking to save money. And so As you go to the right-hand side of this chart, the more you use them, the smaller the delta needs to be before you get an advantage. So today we're going to quickly cover the assumptions, the different types of systems, the results, and some conclusions. One thing that I did here in order to keep it brief is I didn't get into all of the total life cycle costs, which would be the actual maintenance cost of the equipment and the capital cost of buying the generators, the electric motors, and so forth. I just looked at fuel, and we know the other costs are there. So that could be something that, you know, the next phase of this presentation would be one to actually take these numbers and put a life cycle cost analysis together. So we've got an 11-meter hard chine monohull, aluminum construction, 2 drive lines, both of them fixed pitch submerged propellers, just because that's easy, again. 8,250 grams displacement, so it's reasonable. It's not overly heavy. I believe that from the presentation this morning, the 11-meter boat weighed 9,500 kilograms, somewhere in that neighborhood. 30-knot maximum speed. Operational profile, it's a USV, so let's let it work hard for us. Let's let it go out for 24 hours per mission. 5% of that time will be at wide open throttle, so it identifies a target and it's trying to intercept that target. 95% of the time will be at 5% power, so it's just kind of hanging around, it's loitering. In the United States, this is very popular now from what they call port security. This is a real mission. I live in Virginia, which is very close to one of the largest naval bases on the east coast of the United States. And we have, I believe it's at Norfolk Naval Base, there are 7 large ship piers which can house anything from aircraft carriers, submarines, landing platform docks, landing supply ships, and the works. And all of that naval base is exposed by the waterfront to the commercial harbor and to recreational boat passageways. And right now, on any given day, 24 hours a day, there are 4 or 5 small craft manned by personnel with machine guns on them protecting those ships. So when you start looking at this mission as a port security USV, it has real benefits, real uses, and a real life application. One of the assumptions we made was that at 5 knots, the idle speed, essentially, the resistance and the powering of the boats were all the same, the different propulsion systems. However, we did take into account at 30 knots, if you have more weight because of batteries or a generator on board as well, you burn more fuel. We looked at 5 boats in the fleet just because that's how many boats I see when I go past Norfolk Naval Shipyard. I see 5 harbor security boats on station at any given time. I assumed 1 boat would be down each week for maintenance, overhaul, oil change, major events, so forth and so on, whatever the case might be. Useful life of 10 years is probably reasonable for small craft. I'm not sure if we're getting more than that in today's industry, but that's what I just chose to throw together for this one. And that type of operational profile of 24 hours a day, 1 boat down per week for maintenance, that gives you 7,000 annually operating hours. Recreational boats that we do a lot of at Donald Blount & Associates, those see anywhere from 360 to 500 annual operating hours. So you can see the big difference, and you can see we've chosen an application that makes the delta have to be small to show a benefit. This was the types of propulsion system we evaluated, and it's presented here in words. Basically, the first one is a diesel engine. The second is the same diesel engine, but instead of powering it with diesel fuel, we powered it with compressed natural gas. Not liquefied natural gas, but compressed natural gas. Anybody wants to talk about that later and why I chose that, I'd be happy to. Diesel electric is another option. Then we looked at a diesel electric hybrid, which means we added batteries. And then when we wanted to charge those batteries, there's 2 different ways. One way we chose to do it was with a generator, and one of the ways we chose to do it was with a PTO generator, or a power takeoff generator, driven by the main engine in the gearbox. It's a chart, a lot of checks and arrows, hard to look at, so let's look at it from a picture perspective. This should be a little bit easier for everybody. This is these are the illustrations of the propulsion system. This is one side. All these boats had 2 engines, 2 drive lines, but basically they all have the big, large main engine for accomplishing the 30-knot speed. As soon as you introduce diesel electric, you need a generator to provide electrical power. And then as soon as you have the word hybrid, we throw some batteries in here, a propulsion battery bank as well over on the right. And the last one you can see, which was the PTO generator, you can see I put a G in with the M, which means it's a motor or a generator. A lot of the engine manufacturers are starting to start to have products like this. Steyr, I think, was the pioneer, and it comes to mind. They've got a 5 kilowatt motor generator that's comes coupled directly between the main engine, I think, and the gearbox is available from one of their products. So this is the state of charge profile, and this is kind of where it starts to get interesting when you're thinking about the electric side of things. And it sizes the battery bank, kind of, and the generator, kind of. There's a lot of stuff that goes into this. But basically, there's a lot of interesting stuff that's here. And the first thing that I'll talk about is the endurance. So basically, where you see the pink bands, that is where we are charging the batteries. And then you can see the white bands where I've highlighted one of them green. And in this instance, that is where we are actually operating on battery power. So that's the endurance, and that's driven by the battery bank capacity, right? More batteries, bigger batteries, the longer you can operate without charging them before you've depleted the batteries. So the next one is the time to charge, the charging time. Again, that's also driven by the battery bank size, but in addition to that, it's driven by the generator size. A bigger generator can charge faster, as you can imagine. So we start looking at some results. Well, actually, there's one more thing that I should cover here. The blue line is the state of charge. And the idea with the blue line is that that's how much charge is level. It's what's in the fuel tank for the batteries, right? And you'll note here that I go from 30% and then I start to charge it up and I charge to 80%. And some of you might be saying, oh, well, what about the other 50% of the battery you're not using? Well, there's two neat things that go into this. Number one is that if you try to discharge the battery to the 0 to 30% range, what you'll find is that you'll damage the battery and you'll reduce its life. Batteries are expensive, so we need to try to preserve them. And then on the top side, between 80% and 100%, the amount of time, like physical minutes on your watch or your phone, that it takes to charge the batteries from 80 to 100% can be just as much time as it takes to charge the batteries from 30 to 80%. So if you're looking to try to figure out how soon can I turn the generator off and stop burning fuel, you don't want to be charging between 80 and 100%. It's not very efficient. So this is the state of the results. And what we can see here, kind of our baseline, is propulsion system was 1 and 2 at the top. And we'll see that the diesel engine, and whether it be powered by diesel or natural gas, it's on a lot of the time. The numbers really don't mean anything. I tried to color code it so it was a little bit simpler to read. But this is all based on the entire fleet of 5 boats for 10 years of operation. So this is the total life cycle. So that's 700,000 hours on the diesel engine. Okay, so now we've got to talk about replacing diesel engines, because Volvo's good, but they're not that good. And so, you got to take these changes and these costs of maintenance into it. Diesel electric. So now we've got an alternate source. We have the ability to shut the main engines down. And what do you see? We go from 700,000 operating hours to 35,000 operating hours. Okay, so it comes down significantly. The last one is the diesel electric that had, instead of the generator, it has a diesel engine driven generator, a SSDG, some people call it. It takes the power to charge the batteries off the main engines. So the main engine comes back on and you don't save as many hours. So it's still upwards of about 400. Let's see. So generator hours, you can see that when you add the batteries in case 4 relative to case 3, that you cut down the number of annual operating hours of the generator, which that's good because it reduces the generator maintenance cost. Finally, the last two, 4 and 5, you can see over on the far right of the screen that we have battery replacements and number of cycles, and that's the cost of adding the battery into the system. So this is all, this figure is one to talk about maintenance cost, capital cost, and replacement cost. The last two depends on the depth of the state of the charge profile and the depth of discharge, how the designer sets up the system to work. If you have a really small battery bank and you're fluctuating the charge level up and down all the time, then you're going to wear the thing out. So basically, you've got to right size the battery bank, and you have to make sure that you're not being too aggressive with how far you take it down to the depth of discharge, and you don't want to cycle it a lot, and then you'll get greater life out of your batteries. And these are special batteries. They are expensive. It's important to consider. So as I said, depth of discharge. Another thing that goes into it is selected chemistry. There are several, these are all lithium-ion batteries that I've talked about in this presentation. And I actually looked at 5 different types for their advantages and disadvantages. What I found is they're all expensive, and they all are within a certain boundary range. And in that boundary range, you can do certain things, but nevertheless, with today's technology, if we're the black triangle in the middle, with one technology and sizing, I had to change the batteries about 20 times over 10 years. And in another case, I think I was able to keep the number of replacements down to 6 times. So the size of the battery bank and the number of cycles is what defines the slope of the blue line that you see. Okay, so dollars and cents. All right, so the first one is the diesel engine, 52 cents a liter. I know U.S. prices. Sorry, I'm biased. But nevertheless, what you can see, that's our baseline. So over the life of the thing, it's about $3.5 million for the fuel. Compressed natural gas, same propulsion system, no additional capital cost. Okay, a little bit, because a compressed natural gas powered engine is a special thing. But nevertheless, when you look at that, what we see here is there's actually a 63% reduction in cost of fuel in order to burn compressed natural gas, which is pretty darn significant. And that's primarily due to the price of the fuel being so low. You can see that the amount of fuel burn in terms of liters goes up significantly. It's the only red one up there. I went from 7,000 liters, well, 7 million liters of diesel to 60 million liters of compressed natural gas, which as a result produced a lot of extra CO2. So maybe it's not the best thing for the environment because the amount of CO2 production goes up. But on the flip side of it is, it's a very clean burning fuel. There's no soot, there's no particulate in the exhaust, which the school is out there. Some people say it's CO2 and global warming that's the prime factor for consideration, and some people say that it's the particulate in the exhaust and the noxious compounds that it creates with sulfur dioxide and nitrous oxide. Additionally, we have diesel electric, which number 3 was this dedicated diesel engine, and what we can see here is that we do have a reduction in CO2 and we have a reduction in fuel cost, a 20% savings by using that propulsion plant. That's pretty good. If we bring the hybrid in, which everyone probably thinks, oh, well, the hybrid, everybody wants the electric. What do we see here? The hybrid does not provide the same fuel savings as the diesel electric option with the dedicated generator. And why is that? Anybody have a guess? Because of the inefficiencies of the electricity going into the battery, the losses, and then when you come out of the battery and go back into the wires, you have another loss. So you're hit up with a 10% power conversion loss going into the battery and then again coming out of the battery. So while it might make the generator or the main engine or any of the things work better, there's so much loss associated with putting power into a battery and taking it out that it actually kills the technology. But it does give you a silent operating mode, which can be really advantageous to have zero noise emissions, whether it be for wildlife, whether it be for stealth mode, whether it be not to bother your neighbors. We get that a lot in the yachting, the yacht stuff that we do. So there are advantages for all of them, but right now the diesel takes the cake. So let's see. So series diesel hybrid, there's no solution. We talked about that last year, and I briefly touched on it this year. The size and the weight of the motors and the batteries gets so big, and the generator gets so big that it just sinks the boat when we're talking about small high-speed craft. Parallel diesel will work on small high-speed craft, so that's a good thing. But we've got to use it for loiter operation or slow-speed operation. There are certainly plenty of operational profiles with less difference between the high speed and the low speed that we've analyzed today. Today we looked at a 95%, 5% split. And it's very possible that a real operational profile may be 80-20 or 70-30. In any of these cases, the designer must go in and do the full analysis like I've done here in this trade study in order to determine where the crossover point is for it to generate an economic return. All of the options we looked at saved hours on the main engine, which is good. It reduces maintenance costs. Every time you change the oil, it's expensive. The CNG does provide a significant reduction in costs. It is the nearest term solution for reducing costs that's available on a mass scale, but it does have an increase in CO2, which will be frowned upon by some parties. State of the charge profile is very important when you look at the amount of time that the battery is being charged versus discharged, the amount you're taking out of the battery, because if you go too low, what you'll see is you'll damage the battery. And a dedicated generator is more efficient than a PTO in this application. You know, we looked at it where both engines were on and operating at the same time to charge the batteries, but we could also turn that around and say when you need to charge the batteries, you only start one of the main engines, and then you can alternate the main engines when you're charging and further reduce the hours. So there's a lot of different options that can be looked at. This is just one case study, but it does show a positive use of a diesel-electric system in a small high-speed craft. So with that, I want to thank you and take any questions that you might have. Yes, sir. Yes, so the question was this all calculated with DC current? And no. This was all AC. Most of the we actually looked at a comparison as well between a dedicated diesel and for a diesel generator, which are actually alternators, and then the alternator on the front of the engine. And what we found was that the generator for the generator is actually about 30% more efficient than the little alternator that's on the front of the boat. So it's all AC current, and it does have it take into account the change from AC to DC and back. Yes. Yep. Yes, sir. Yes. Yep, you get a performance, you get an efficient, sorry. So the question was, did we take into account the difference in engine efficiency between when it's operating at idle speed or at idle speed with the power takeoff where it raises the loading on the engine? And the answer to the question is yes, we did. I think it was, I've got my cheat sheet slide up here, guys, so sorry about this. It looks like we reduced the fuel consumption in terms, specific fuel consumption by about 10% by doing that. But we're so far down and the loads are so low that while there is an improvement there, you lose it all by going through the batteries. But we did take into account. Good question. Anyone else? Yes, sir. We did not consider solar power for this particular project. I've done solar power before on a 4-knot vessel. It was an oceanographic research vessel, and it was designed with the ability to cross the Pacific Ocean. It was one of the mission statements. And in order to get enough solar panels to go 4 knots continuously, 24 hours a day, I ended up with the boat was 7 meters long. My design was 7 meters long, and I carried 2,200 kilograms of batteries. This was lead acid batteries because I did this project 12 years ago, but we actually built the boat and put it in service. So real life experience says that it's not practical. Technology has come a long way since then, and perhaps solar is a lot more efficient now. And likewise with lithium ion, I think there'd be some improvements as well. That would be a good one to go back and look at. Thank you very much. I appreciate your attention.